spent a good amount of time on the first page. Lots of important stuff there. We'll repeat these ideas moving forward. Let's see how we did on predicting the major products. How are we doing on the first one? Example reactions. We're doing, what are we doing? Let's see, I'm not sure. Roman numeral 1, addition of HX to give alkyl halides. That's what we're doing. Okay, pick the product. How do we do on the first one here? How's that look? How'd we do? Any questions about that one? No? How about the next one? How'd we do? Do they have a product for the next one? Amber, what you got? Yep, good. Anybody else? Boom, 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 boom. Iodine there, right? Questions? How we do? Questions about the first reaction. Is the first reaction regioselective? Did you say regioselective or no? Yeah? Yeah, the first reaction should be regioselective. How about the second reaction? Regioselective or no? Yes, second reaction should be regioselective. Everybody with me? How about the third reaction? Have a product for it? What did you get for the third one?
It's not regioselective, right?
So why did you show only one product? Yeah, the third reaction is not going to be regioselective. Everybody here? All right, boom, 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 boom. We could have iodine here, or we could have boom, 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 boom. We could have iodine here. Any questions about those three? All right, synthesis. Everybody good with those three? I don't believe you guys. I don't believe it. Good. All right. I see a lot of people who have nothing written down. Who attempted these before class today? You all have to attempt problems before class or you're not going to learn. Okay? You have to ask questions. I can imagine that 95% of you do not understand any of that we just talked about, but nobody raised their hand. That means you do not have questions. Okay, experiment here. How prepared are you guys to do this, and how willing are you to ask questions? So I'm gauging that. How are we doing the first one, guys? Let's look at it. Okay, I hate to walk you through this, because that's not good. All right? I'll walk you through the first one, then I want you to do the next two. But again, this is what we said last time. You need to come prepared, look ahead for questions, and be ready to discuss. Alternatively, we could say, turn these in next time you come to class. But I'm not going to do that. All right, first reaction, what do we have? We have an alkene, we have H+. Okay? This can be shown covalently, all right? Or it can be showed ionically, either way. H+, Cl-. Boom, 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 boom. Alkene, electrons. Electrons attack the electrophilic H+, either way. We're going to pull away and we're going to leave cation. Are we going to leave cation on top or bottom? Cation on top or bottom?
Top.
Where did we leave cation last time?
Tertiary carbon.
Tertiary. Versus, what was the other choice?
Secondary.
The other choice was actually primary last time. Which is preferred, primary or tertiary?
Tertiary.
Tertiary carbocation preferred. Okay? Would you rather leave cation at top or bottom? Cation at top will be tertiary. Cation at bottom will be secondary. Which is better?
Tertiary.
Tertiary. We're going to leave cation at the top. That means the double bond pulls away from the top and goes attacks the H+. Okay? Boom, 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 boom. Boom. Go attack the H+. What do we leave up top?
Cation.
Carbocation. All this should have been done, though, as homework. Thought process, homework. You're ready to go today. Because we're repeating the same thing we did on the previous page. Same ideas. Cation, this is your carbocation intermediate, okay? Regio selected because tertiary is favored over secondary. The other one would be secondary. Can you draw it? You should be able to draw it. What happens next? Then the Cl- attacks the cation. Bam. And what do we get? Well, I've already showed the product, right? Boom, boom. There we go. We showed that product. Where's the new H at here? New H is here. Now, often my bonds won't connect. 6-member ring. New H here, right? We've added HCl across the double bond. HI, what are we doing? Alkene reactions, they react with HX to form what type of product? What type of product do you get when you react with alkene with HX?
Hydride.
We discussed it yesterday. You got to come to class, know that today. All right? What it is again?
Hydrohalogenate.
Hydrohalogenation, the process. What's the name of the type of product we get?
Alkyl halide.
Thank you. Alkyl halide. Okay, what alkyl halide are we going to make here? Where are you going to make cation? That's the question with all these alkene reactions. Where are you going to make cation? Assuming we're going to have a cation formed. Where are you going to make cation, left or right? You can on the left, it'd be secondary. You make cation on the right, that would be primary. Okay? So we attack the H+. I'll show it covalently here. We attack the H, kick off the iodine. All right, here's the double bond. Go make a bond to H, kick off the iodine, leaving this carbon over here as a cation. Boom, 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 boom. Bond to H, leaving the carbon over here as a cation. And then the I- does what? These electrons attack the cation, and we get the final product. Boom, 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 boom. Iodine here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Iodine there. New H on the end, right? going to get cation on the right carbon? Are we going to get cation on the right carbon? No, why not? Boom, 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 boom. Are we going to get cation on the right carbon? Primary, no. Secondary is better, right? Okay. So is this reaction going to be regioselective? Is it going to select for this product here? Only way the iodine is going to get here is if the cation formed there. Because iodine, you get it from iodine attacking cation. Are we going to get product with iodine on the end where it attacked there? No. Thus, this reaction is said to be regioselective. Same way with the first one. This first one was regioselective. You're not going to get the regioisomer. All right? The other would be boom, 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 boom. Iodine on the end would be regioisomer. The iodine is bonded in different regions. But we're not going to get that. The product is going to be selective. Reaction will be selective for this regioisomer. The reaction is regioselective. This reaction is regioselective. How about the one at the bottom? Where are we going to make cation at? Right or left? Cation on right would be secondary. Cation on left would be secondary. Which is favored? No preference. No preference. Actually, two possible products down here because there's no selectivity. We're either going to get H on this and I there, or I here and H there. And so we know our mechanism. Either iodine here or iodine 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, or iodine here. Either 2-iodopentane or 3-iodopentane. Why would one be favored over the other? It's all based on carbocation. There's going to be no preferred carbocation here. This reaction is not going to be regioselective. Note the two reactions here. The second and third reaction both give 2-iodopentane. I'm sorry, that's not 2, that's 3. 2-iodopentane, right, same compound, right? They both give it. But the second reaction gives it selectively, where the third reaction gives two different products. If you wanted to make 2-iodopentane, which reaction would be better? If you wanted a high yield of 2-iodopentane, which reaction would be better?
First one.
The second one of the three. First one of the two. This one would be better. It's more regioselective if you want that product. If you want 3-iodopentane, well, this is the only way to make it from an alkene reaction. It's going to be more difficult to make because it's going to give some of this as a side product. If you want to purify this, then you're going to have to separate it, distill it. Now, when we say regioselective, that does not mean that this does not give any of the other possible product. It's just it's going to be highly selective for this one. Where this one we expect no selectivity. It may be 50-50 or it may be 60-40. It's hard to say, but we have no basis for saying one of these is favored over the other. Synthesis. Synthesis is going backwards. How do you make compounds? Okay, guys, I've started off here because I'm kind of giving you a warning. You're going to get left behind if you don't come prepared. All right? Future, we're going to be moving ahead. You're going to be sitting there. You got to come prepared. You got to work ahead. Okay, the outlines are there. It says provide the product. That means homework. Provide the product. Okay, synthesis. Provide a high yielding that is regioselective synthesis of the following alkyl halides. using a hydrogenation reaction, which by the way is the only reaction you know thus far. By the end of organic 2, you may know multiple ways to make this compound. Right now, you only know one reaction. By the end of this class, you'll know multiple ways to make such a compound. So, going backwards, what alkene would we use to make this? There's only two choices. Can you show the two choices? We can either have this alkene, because we know when we add HBr, we wanted to use HBr, right? Not HI or anything. It's obvious. Then we're going to add an H to one carbon and a Br to the other. So we can get a Br here and an H here. By the way, we do need an H here if we start with an alkene, because there's 2 here and there's 3 there. But we could also use this alkene, because we could envision maybe adding Br here and H here. And if we did that, we'd also get that product. By the way, nomenclature, how we did on that. Name of this compound. 1-pentene. Name of this compound.
I can't hear guys.
2-pentene. Everybody watch nomenclature video? This compound needs more to the name though. In addition to just 2-pentene, what else would you call it? All right. Which one would be best to make this compound here? And when we go backwards, we use a double-headed arrow. This means we're going backwards. It's called a retrosynthetic or retrosynthesis arrow. Going backwards. Where would you like to go backwards to as a starting point? Which would be better? Top one. Why? Yeah. React this with HBr. Or would we get that product? Now this means we're coming forward. Would that be regioselective? Where are you going to make cation at? Left or right?
Right.
On the right. Selectively or no? How about here? Cation on left or right? Either one. It won't be selective. Okay? That reaction is going to be regioselective. This will not be. Okay, if we come this way, it won't be regioselective. It'll be lower yielding. You'll get a mixture. Unless you want a mixture, that's not good. How about over here? Can you show a reaction that would give that product? Basically, what alkene would you react with HCl? Clearly, you got to use HCl, right? Not HBr. What alkene would you propose to react with HCl to give that product? Anybody have an alkene? That's right. 1-methyl cyclohexene. That's cyclohexene 1-methyl. I'll draw it over here. Yeah, I think I'll turn it a little bit. Double bond there. That's cyclohexene. That's 1-methyl cyclohexene. Okay. React that with HCl. You're going to get that product. Where are we going to make cation at? Left or right? Left. It would be tertiary. I know not everybody has seen that. You got to make sure when I say left or right, what am I talking about? And when I say tertiary, what am I talking about? All right? Be tertiary. Because I can't draw the cation every single time. We'll be drawing cations a million times between here and next week. And then the chlorine attacks the tertiary carbocation, right? All right? Yeah. That'd be a good reaction, regioselective. There's another possibility though. Anybody got another reaction that would give this? Can the double bond be on the other side? There? Well, that's the same compound. It's the same compound. Both of these are 1-methyl cyclohexene. So it's a repeat. Is there another? There actually is. What if we have the double bond up like this to that carbon? Would that, where are we going to make cation? Top or bottom?
Bottom.
Bottom would be tertiary. Top would be primary. Draw both cations. Prove it yourself. Cation on top, okay. React this with ACl, and that would also give that product. Both of those would be regioselective because you have tertiary cations versus either primary or secondary. Which product is favored in the following reaction? Please think about that one. Please think about that one. Okay, that's a look at adding HX to alkene. Moving on to Roman numeral 2. Next we're going to add water to alkenes to give what type of product? Alcohols. Not alkyl halides, but alcohols. And this reaction, when you add water to a molecule, it's called what? Typically hydration. Hydrolysis is when water, lysis. Lysis is breaking. Breaking it apart. Just adding would not be a lysis. Hydration. Adding water. Hydration. Hydration of an alkene. Let's look at that. Right here. Yep. No, that is it. What was I looking at? Oh, the top is okay. Alkenes actually do not react with pure water. No reaction. Water is not reactive enough. It's not electrophilic enough. Here's the pi bond. These electrons are ready to do something. They see water. They're like, whatever. Okay? They're not, but they see proton, H+, they're like, ooh, proton. Okay? H+ is not acidic enough, it's not electrophilic enough, no reaction. The skin of an apple contains lots of alkene compounds. Does the skin of an apple react with water when it rains? No, it actually protects the apple, the inside of the apple, because the alkene does not. Acid rain, on the other hand, you start having some problems, because now you've got acid. If we take water with acid, we can get a reaction. And we can add water, essentially water to the alkene, and acid serves as the catalyst here. We've added water. If you look at the formula, we've now added H2O to the formula. So it's an addition reaction. Here's the OH. Well, where's the other H of a water? What's on the end here? Because that carbon has 2, but now the N has 3. So right here is what we added across the pi bond. That's H2O. So we've essentially added water. So you got to understand and see what we're doing here in terms of our product. Water's added, it's addition reaction. H+ is a catalyst. Now, importantly, how do we show water in H+? A lot of times we could show it like this, or we could show it combined as H3O+. When you see this, you have water and H+. Well, what is H+? Acid, but exactly. Here's a little caution for you. If you go to the stockroom and ask for H+, they're going to look at you funny. What do you mean H+? Well, H+ is a generic indicator for acid. What acid? What acid do you want? Example acids are sulfuric acid, phosphoric acid, HF here. Okay? This is typically a strong acid. Although it doesn't have to be the 7 strong acids you saw in Gen Chem. Phosphoric and HF is also strong enough. Okay? Importantly, though, it cannot be like HX. It can't be HBr. Because if you have HBr in an alkene, you're going to get a different product. You'll get an alkyl bromide. HX reacts with alkenes in a different manner, so you don't want to use that acid. These acids you use as catalysts because they will not react with the alkene in any other way. At least not in this class. All right? So let's look at the reaction down here. This reacts with aqueous sulfuric. Well, what is aqueous sulfuric? That's just, ultimately, this is H3O+, right? This is aqueous acid. That's aqueous acid. Well, this is aqueous acid, water and acid. Lots of ways you can show this. Ultimately, though, it's acid and water. First step of this reaction is reacting with the H+. Just like the first step of the previous reaction. Except here, I'm just going to show it ionic. And it's okay to just show a lone H+, although we know in real life that it's usually coordinated with like water or something. Okay? But we can show H+. Alkene attacks H+. Where are we going to leave cation at? Right or left here? We'll leave cation on the left. Okay? So the pi bond attacks the H+, makes bond to H+, leaving that carbon as a cation, tertiary carbocation. The next step. Previously we had a halide to attack the cation, like a Br-. Here, water attacks the cation. So these electrons from water make bond to cation. And now we have oxygen bonded to carbon. The oxygen now is a positive charge. The oxygen also has 2 H's. We don't lose 2 H's when we make the bond between oxygen and carbon. We lose one of them in a next step. Next step is something has to take the H and give the oxygen its lone pair back. The conjugate base of the strong acid, I typically show doing that. Also, I typically will allow you to just do this condensed, sort of just like this. Now, if we draw it out, we've got this is really this, right? You say these electrons bond to the H. These electrons move on to the oxygen. What does that give? It gives our final product. Now the oxygen has 2 lone pairs. Now the bisulfate is now bonding to the H again, and what does this produce? It produces H2SO4. But that's what we started with. And that's why we call it catalyst. Because the catalyst is reformed at the end of the reaction. And ultimately, we have added water to the alkene. Again, because the formula now contains H2O. Now, I do it like this. This is actually not strictly correct. It's actually more correct to use water to take this proton. If water takes the proton, you'll get this plus what? Plus H3O plus. If water takes the proton. That's actually strictly more correct, because how does aqueous sulfuric acid actually exist? It actually exists like this. This is aqueous sulfuric acid. It's ionized with water. See, if I use water to take the proton, I'll get this, because water will become this. And this guy will do nothing. It'll just always be the anion. But I actually like to use the conjugate base of my strong acid and reform the actual acid. I tend to prefer to do that. But you can use water, because the proton sits with water anyway. This is a hydration reaction. It only occurs with the H plus catalyst, and the first step is the alkene attacking the H plus catalyst. The H plus. Also in my reactions, typically I will show the added electrophile here. That does not mean it's there. How many H's on that carbon? 3. 2 there. There's now 3 here. I drew in the new one. There's still 3 here. I just no longer drew in the new one. That's typically how I will do it. I sort of indicate the new one here. In books, though, they may not indicate it. They may draw this as, there's your cation. You just have to know that there's a new H out there. Hopefully you know that, because you just made a bond to it right here. That's a hydration reaction. Importantly, though, do you see the consistencies with the HX reaction? The difference is here you have a different nucleophile. This is also acid catalyzed, because you have to regenerate the acid. Because the nucleophile, after it adds, you have to lose an H. Where in the HX reaction, we didn't have to do that. Reversibility of this reaction, this is just a miscellaneous comment. But this can be reversed. You can take an alcohol with an acid catalyst, and you can go back to the alkene. Now that's not a hydration reaction. That is a dehydration reaction. Yeah. We'll actually look at this type of reaction during test 3. It'll be just the opposite. But guess what? The mechanism is already there. It's just doing it reversed. That is, you start with your alcohol, and what's the first intermediate you form? The protonated alcohol. You put the proton on the oxygen. Then water leaves to make a cation, and then you lose this beta hydrogen to make the alkene. You just go the other way. Guess what? Once we learn the forward way, then the opposite way is going to be easier. Okay, that's just a miscellaneous comment. Predict the products. Including stereochemistry. We'll need to talk about the stereochemistry there. Okay, we'll see how we did on those on Monday. Roman numeral 3 is sort of in those problems. Okay. Roman numeral 4, carbocation rearrangements. Let's look at this reaction. If we take this alkene, react with HBr, the major product is this. Minor product here. If I hadn't showed you any products, hopefully you would have predicted the minor product. Let's see, this attacks H, carbocation, top or bottom? Bottom, and then Br minus attacks carbocation to have bromine bonded here. Well, that's this product here with a new H here. Always got to know where your new H's are at. New H there, new bromine here. Used to be pi bond. But in this case, this is actually the major product. The bromine ends up bonded over here. How does that happen?
Just places with the H on them.
It's a carbocation rearrangement. What'd you say?
Changes place with the hydrogen on that.
Well, a lot of the answers in the heading, as it usually is with me, because the headings are very important. This is a carbocation rearrangement, and it occurs by a 1,2 hydride shift. Okay, let's look at the mechanism. We got H plus and we got Br minus. Alkene is going to attack H plus. Okay, here's the alkene. I'm going to break away from the bottom carbon. So it's sort of going up and attacking, all right? So somebody pull my arm up, yank it up. That's what I'm doing here. I'm trying to yank this up. All right, here we go. Yank it up in this direction. And what are we getting here? Boom, 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 boom. Which carbon's now bonded to an H? All right, you got to see that. That carbon is, look. Burn. This carbon is now bonded to the H, leaving this one with no bond. This one's a carbocation. If Br minus added here, we would get that product. How do we get the other product? First off, we need to sort of take stock here. How many H's on this carbon? 2. How many H's on the carbon there? Only 1. How do we get another H here? Because this didn't add 1 there. 2 H's there. Now 3. But we have 3 there now. Only 1 H here. How do we get 2 there? Because the final product has to have 2. Where does the other H come from? Well, also, let's look at this. How many H's on this carbon? None. How many H's on this carbon? 1. We got to lose an H from there. Then we got to get an H over here. Let's draw in that H. This H migrates over. It's going to migrate over. We'll do the mechanism, and it's going to give this cation. We'll do this. But once we get this cation, can you see how we get this product? Because then the Br minus, which is floating around, I shouldn't have even redrawn it. These electrons attack here, and there you go. That's how you get your major product. But let's look at this right here. This is a carbocation rearrangement, but here it's secondary, and it rearranged to a tertiary carbocation. Mechanism. The electrons here is a sigma bond. But sigma bonds can also be sources of electrons that do reactions. Not as often as pi bonds. But these electrons become attracted to this neighboring charge. And they can essentially break free of this carbon. Here we go. Let's break it free of this carbon and move it over and bond there. So I'm going to yank it over, these two electrons, and move them over and bond them here. Let's draw in the new H. And now we get a new H over there. Now this is called a 1,2 hydride shift. Because if this is 1, if the H is on the 1 carbon, where does it end up at? If that's 1, it ends up on the 2. Now this is not nomenclature. This is just the starting point is 1, it ends up 2. If it started here and ended up there, we'd call it a, not a 1,2, but it'd be a 1,3. Okay? It's just positioning, beginning and end. A 1,2 hydride shift. Why does it do this? This is secondary. Did it become better? Did it become a better cation? Yes. Rearrangements typically occur, carbocation rearrangements occur to give better cations. And this can happen. Let's act this out, shall we? Okay, here we go. I'm the H bonded to you. And there's a cation next door. Okay? And you're currently secondary. Okay? And you're tertiary even when we make the cation. Here's a cation next door. These are electrons, CH bond. But they're going to be attracted to cation. And eventually the reaction that takes place is, they're like, okay, sorry, I like you, but I'm going this way. I break free and go over here and bond to this carbon. Leaving you as you have a cation. Right? I'm going to break free and go bond over here because you can handle it. You're tertiary. She needed some help. She wasn't as stable as you're going to become. Things become better. Okay? That's what drives this. You don't get rearrangements to worse cations. You only get rearrangements to better. Usually the substitution is the main way. We'll see another way, like ring size. Okay? There we go. And this is your mechanism. You air these two electrons. Why is it called hydride? Well, we're moving the H nucleus, but also the two electrons. Two electrons in the covalent bond are moved too. And it's like the H and two electrons. But this is hydride. By the way, that'd be a minus charge if it was by itself, because it's hydrogen anion. What do you call a chlorine anion? Chloride. What do you call a bromine anion? Bromide. What do you call a nitrogen anion? It's actually called a nitride sometimes. What do you call a hydrogen anion? Hydride, okay? ID ending indicates anion. Do you see how we get major product? Comes from a hydride shift. But you can also do alkyl shifts. Now, this is essentially the same thing. We don't call it alkylide. Okay? It might be good to call it alkylide because this is the same idea. It's a carbanion moving, but alkylide is just the term that's not used. If it was, it would make sense. Okay, let's see where we're at. Try the reaction below. Okay. Including looking ahead, and also give the TAC a try. Okay. That mechanism. I need to start looking at that. I see some of you in lab this afternoon, guys. Have a good day.